Hello and welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video I will tell you about random forests in a nutshell. In the end, you should understand the basic concept of a random forest, you should know some basic aggregation rules and understand at least a basic concept of feature importance. What is a random forest? You already know tree learners. And with random forests, we try to stabilize those tree learners by bagging. Bagging is short for bootstrap aggregation, and I will explain you what bootstrap aggregation means. So what happens here is we have, again, labeled training data set with 3 observations, 3 features, and 1 categorical target variable. So what Bootstrap means is that we generate new training data sets out of the one training data set that we have. Yeah, so we cannot magically come up with new observations. So what we do is we just draw with replacement from the training data. So if you look at the first Bootstrap sample, that it has also 3 observations, such as the original training data set, but not all of these observations are different. Okay? The observation with age 23 comes up twice, and the observation with age 70 is missing. Okay? And the observation with age 48 is there once. And we do this several times, let's say m times. And in other Bootstrap samples, other observations may be apparent more than once, such as the 70, age equals 70 observations here in the last Bootstrap sample, and others may not show up at all in this Bootstrap sample. What we do then is we take these new data sets, and for each data set we learn a tree, separately and independently of the other trees. So this means we get a lot of trees. Well, that's why we call it forest in the end. So we have a lot of trees, and all of these trees are learned independently from each other. So when we have a new observation coming in for prediction, of course we have to decide, well, what do we do with it? So we pass it through all the trees, and then in the end we need some aggregation rule which tells us how we average the predictions of the different trees. And that, in the end, is the entire random forest model. Random forests can be used for classification and regression, because then as base learners we just use classification or regression trees. And as already said, at prediction time nothing really fancy happens, because we have just learned a new supervised machine learning model. So this picture here is the same as usually always, just in the middle we have a random forest model instead of a tree learner, or instead of a logistic regression, or instead of whatever else. Okay, so the fancy part is in the training part. In the prediction, it just looks and feels like any other supervised machine learning model. Okay, I already said if we have several trees, then each tree may give us a different prediction, and now the task is to aggregate the predictions of the different tree learners. So let's start here on the left hand side, where we treat a classification task, which means the target variable is a categorical variable, in this case level of happiness again, and we have one observation which we try to predict. So we feed this prediction through all the trees. We feed this observation through all the trees. So we have 5 trees in this example, and each tree gives one classification. Okay, the first and the 5th say it's pretty happy, and the other 3 say it's not too happy. So what we can do is taking a majority vote of these. So we have 3 trees voting for not too happy, we have 2 trees voting for pretty happy, and we have no tree predicting the 3rd category. So with taking the majority vote, the final random forest prediction is not too happy. Then on the right hand side we have a regression task. So this means the target variable is a numerical variable, and again we feed all the features through all the trees. We get 5 predictions. Each tree has a unique has its own prediction, and what we can do is, for example, just take the average, so just the arithmetic mean of the predictions of the several trees, and then we end up with one random forest prediction. That's example, it's 484.2. Okay, whatever, just some number, but it's the empirical, the arithmetic mean of those 5 individual tree predictions. One note on the performance of random forests. So, well, what's not on the slide, but what's also very important is that random forests usually tend to perform really, really well on tabular data sets. It's hard to beat a random forest. Very much later you will perhaps see some boosted trees. These perform very well as well, but random forests are quite well-performing models. So that's perhaps the most important part here. In general, there's one rule: increasing the sample size stabilizes the predictions, which you perhaps can see somewhere here. So on the left-hand side, it's just one tree. On the right-hand side, we have 50,000 trees, which is too much usually, but it is somehow this stabilizes the prediction. But still, sometimes for regression tasks, the stabilization is often not sufficient, which means that we need some more tricks, which you will learn about, of course. But for classification tasks, this works quite nicely. So if we first just have a look at the second row here, we have binary target variable 0 and 1, circles and triangles, and you see the decision regions of 2 random forests. These are a little bit different. You can barely see it because they are so similar, which is good. So they are different because, well, the random forest has 2 random components. That's the bootstrapping and one thing which I tell you about on the next slide. But still, in the end, they are pretty similar, okay, which is good. And what in the first row here is the visualization of 2 different classification trees. And what is that they are quite different. Okay, if you look at this area here, we have a totally different prediction, and this can happen super fast. If just one observation changes, the entire tree structure can change. So they are very unstable, and random forests remedies this problem of tree learners. Okay, now the second trick I told you about on the slide before. So what we try to do is we try to decorrelate the trees. So we have different trees now, so different votes, let's say, and each of these trees makes mistakes, of course. But we want those trees to make different mistakes, because if each tree makes a different mistake, we can get rid of this problem by averaging out over the predictions of all the trees. But if all the trees make the same mistake, then averaging doesn't help at all. Okay, so we avoid this correlation by 2 things. It's the bootstrap sampling, so drawing with replacement from the training data, and by randomizing splits. Okay, what's randomizing splits? You see here a node of a tree. So here's the parent. Data feed here in, and here we have some child nodes. And what happens here is that in this node, let's start here, we have 6 features available in the dataset: marital status, health, age, sex, and degree. And when searching for the best split in this node, we do not search over all possible features, but first we randomly draw some of those features. So how many features we draw is then a hyperparameter. Let's say we draw 3 features here. So we have a random selection of the features, and we just search for the best splits inside these 3 features. And we do this for every node in every tree. So we take a new sample in every node in every tree, which also decorrelates the trees. Last but not least, there is a nice thing called feature importance. So the question we try to answer with feature importance is, okay, well, which feature is most important for the prediction, for the model, of course. So as you perhaps know from statistics with, I don't know, some p-values, or you want to know how important is the feature. And feature importance are the thing to go with random forests, and there are several options to do feature or to compute feature importances out of random forests. One example is here. That's the feature importance based on improvement in the splitting criterion. There are other, and you will get to know those, but that's just the first glimpse of feature importances here. So how does this work? We have still different trees. So each row here is one tree. We have in total m different trees. And now in each tree, if we want to know the feature importance of the feature health, we look in each tree for all the nodes where we used health as splitting feature. Okay, this may be 0, 1, or several, but it can be can be several nodes where we used health as splitting feature. And then we compute how much this single split improved some quality measure, which you will know about later. But so the question is, how much did this split, and just only this very split in this very node, improve some quality measure? Then we add up all those improvements for the tree. Then we have the improvement from one tree, and we do this for all the trees, sum those up, and then we have a final feature importance, which tells us, in this case, how important the feature health is for the model predictions.